The most common type of evaporator is an air cooling evaporator. Air cooling evaporators are designed to absorb heat from the air to reduce the temperature within a space. In most refrigeration applications, the air is actually a secondary coolant that is then circulated by fans to cool something else. For example, the San Joaquin Valley of California is well known for its agriculture. Fruit harvested in the summer months must be cooled as soon as possible to extend the shelf life. Employing air cooling evaporators for this purpose is common. Still, the goal is not to lower the air temperature, but rather to reduce the temperature of the fruit or vegetable being cooled. The first generation of air cooling evaporators were simply bare pipe coils in which cold saturated liquid would circulate. Without the assistance of a fan, these coils would provide cooling due to what is called natural convection. As air comes in contact with a cold pipe, its density will increase, causing it to fall to the ground and allowing warm air to replace it. As this process repeats, the result is a natural circulation of air without the assistance of fans. As you might have imagined, however, natural convection using bare pipe coils was not an efficient means of cooling. Engineers discovered that the rate of heat transfer is correlated with the heat transfer surface area. To take advantage of this, metal fins were added to the pipes, substantially increasing the surface area of the evaporator. However, while the fins increased the surface area, they also restricted air movement. To address this, fans were employed to force air through the evaporator instead of relying on natural convection. Finned coils and forced air movement are almost exclusively used in air cooling evaporators today. The spacing of fins will vary based on the application of the evaporator. Evaporators used in high temperature applications, such as a loading dock, may have 8 fins per inch, whereas evaporators that operate below 32 degrees Fahrenheit will require much greater spacing to prevent ice from bridging the gap between fins and blocking airflow. Low temperature evaporators will have fin spacing closer to 3 fins per inch. Often, air cooling evaporators are packaged within an enclosure which includes fin tubes, 1 or more fans, and a drain pan to collect water that condenses on the coil's surface. These evaporator units come with connections so that liquid, vapor, and defrost pipes can be directly connected to the evaporator. Air cooling evaporators are categorized as forced draft or induced draft. Induced draft evaporators use a fan to pull air through the fin heat exchanger. The advantage of induced draft evaporators is that this method provides excellent air distribution across the cooling coil. The downside is that the heat from the motor is distributed into the refrigerated space with the air from the fan. Forced draft evaporators also use a fan, but this time to push air through the cooling coil. The pros and cons of forced air evaporators are the opposite of induced draft. The advantage of this approach is that heat from the fan motors can be absorbed by the evaporator before distributing the air throughout the room. Forced air through the coil, however, does not result in a uniform distribution of the air across the coil, which is a downside of the forced air approach.
All right, let's talk about evaporators and kind of how they've progressed over time. So what I've drawn here on the whiteboard here is just a simple bare pipe coil. We have cold liquid refrigerant entering the coil, and imagine it's circulating through this pipe and exiting here at the top as a vapor. So as heat from some product comes in, or heat from the air comes in contact with the pipe, that heat gets transferred into the refrigerant, causes it to boil and exit as a vapor. And believe it or not, this does do refrigeration. It's not a problem. In fact, cold air as it hits or warm air as it hits this pipe will get more dense and will kind of fall to the bottom, creating kind of a natural convection. That's where we get the term hot air rises. Really, it's the dense cold air that's falling. But it's not the most efficient way to exchange heat. So engineers and evaporator designers early on learned that if we add fins to our evaporators, I'm going to draw my fins on here. That this would drastically increase the rate of heat transfer. And that's because we've just increased the surface area. So instead of the air only contacting the tubes, now it's contacting the tubes, and the fins. The fins are made of thin aluminum or some conductive metal. Therefore, as they touch the tubes, the temperature gets uniform across those fins. So now we have this great heat transfer area. This much improved our heat transfer, but we're still relying just on natural convection, just that movement of air all on its own. So the next step in the process was, hey, let's add fans to push air or pull air through the coil. So we put a fan here, and if I draw my arrow this direction, we're now pulling air through this coil. We would call that an induced draft evaporator, air cooling evaporator. If I reverse the flow direction arrow here instead, and I'm pushing air through the coil, we call that a forced draft air cooling evaporator. And those have their pros and cons. The forced draft evaporator, the good thing about it is the motor, which has heat associated with it. I'll draw my motor in here. There's my motor. The heat from the motor gets pushed through the evaporators. That heat gets absorbed into the evaporator before it gets, distributed out to the room. The downside, however, the air doesn't get quite as evenly distributed as it does in an induced draft. So again, I'll flip my arrow back again as we show the air now getting pulled through. The downside here, that heat from the motor now is just getting broadcast into the room without first passing through the evaporator. But the plus side, we get a better distribution across the face of this coil, so more effective use of the entire area of the coil.
Many air cooling evaporators are suspended directly from the ceiling. These ceiling suspended units are typically packaged for this purpose. It is vital to ensure that the building is designed to carry the weight of the evaporators before they are installed in this manner. A downside of ceiling suspended evaporators is that they often require special equipment, such as a scissor lift, to access them for service and maintenance. When a building is not designed to support the evaporator, a dedicated support structure anchored to the foundation can be used to support the evaporator. Another approach is to install an evaporator inside a small room on the roof. This room is typically called a penthouse and is well insulated so that minimal heat from the exterior enters the penthouse. Penthouse evaporators are easier to access than their ceiling suspended counterparts, and they do not occupy any valuable real estate inside the cold room. The downside of a penthouse evaporator is that they are more expensive than a ceiling suspended equivalent. Air handling units are a unique type of air cooling evaporator that are typically installed on a roof, but can also be ground mounted. Air handling units have a finned coil like other air cooling evaporators. What makes an air handling unit unique is that the unit will have other sections to handle the air for a specific purpose. For example, in addition to the cooling coil, an air handling unit might also have a heating coil, a humidifier, a filter bank, and a makeup air damper. Air handling units are employed in situations where precise air quality is required. Bunker-mounted evaporators are less common, but are still widely used in agricultural facilities that employ forced air pre-cooling. A bunker-mounted evaporator is mounted behind a bunker wall. Fans are installed above the coil on the wall, which pull air through the coil openings at the bottom of the wall. The terms blast freezer, spiral freezer, and instant quick freeze, or IQF, are terms applied to evaporators that rapidly cool and freeze a food product. Often, the air cooling evaporators used in this application will be installed inside an enclosure that also has a conveyor belt that carries the product being cooled. The product enters the enclosure warm and leaves a short time later fully frozen.